Okay, today is a kind of a good news day. We're just gonna work this problem. We've got a video, and then you don't have any homework. So, I'll get it right off. All right, now, this problem. I promise you, this problem is going to be on the test, okay? Make sure that you can understand how to work this problem. The only thing I can do on this problem is change the numbers, okay? So, here's the setup. You've got a golf ball up here, certain mass. It's gonna fall from a height of 1.85 meters, it's gonna hit the ground, and then it's gonna bounce up to a height of 1 meter, because we lose some energy during the bounce, okay? So, there's a whole bunch of things that you want to do. Draw a velocity time graph, figure out the force, all of this stuff. So, here's what's going to be important. And I'm not going to change this on the test, we're going to keep these same parameters. Going down is going to be a negative value, anything going up is going to be a positive value, whether it's displacement, force, acceleration, whatever. So, if you visualize this, here's the ball, boom, it's going to hit, it's going to bounce back up. So, let's start with the velocity time graph, okay? So, the ball is here, boom, got this. What's the velocity, where's the velocity time graph going to start?
Zero.
Zero.
And it's gonna slope down.
It's going to slope down,
C, right? Because
Oh, wait, yeah.
down's
Because
negative, right?
it's approaching
down is being defined as negative,
Yeah,
Yeah.
negative 5.8.
The reference point would be,
and the slope is
Negative
Negative.
9.8.
negative 9.8 meters per second squared. Why?
because
Acceleration,
gravity.
that's gravity.
And that's the only force acting on it, right?
C,
So is the momentum changing as it falls?
no. Well,
Yes.
yes.
Of course it is, because velocity.
Yes, because acceleration.
Yes, because the velocity
acceleration
is
I was
changes
changing.
the
testing.
velocity.
I was testing.
How'd they do?
Not very good. Everybody said no.
Okay, quit
No.
bouncing
I took a
your
second.
feet. So, this is gonna be important. At this point, the ball is gonna hit the ground, okay? So this is when it's gonna hit. What's the sign of the velocity when the ball hits the ground?
It's gonna start.
Negative?
Negative, right? I don't know what the number is. I just know when it hits the ground, it's gonna land with some negative velocity,
Yeah.
okay? We'll figure it out later. At this point, I don't care what it is, okay? I just know it's gonna hit with some negative velocity. So when it hits, this is the point that it hits. What's the line gonna do at that point?
Start to have a huge uptick. To
Will it go up steeply or will it go down steeply?
Up steeply.
Up steeply, why?
Because it's going to
Hit the
It's
ground.
gonna do a massive.
It's gonna hit the ground, right?
It's gonna hit the ground.
It won't go
stop,
all the way up there.
Then
Wait, yeah, it will. I lied.
it'll keep going, but it'll be
Whoa, hold on, back up the bus.
gonna.
So, while it's falling, it has negative velocity and negative acceleration, right?
Yeah.
Means it's gonna speed up. So when this ball comes in contact with the ground, what does it begin to do? Slow down, right? Now, if this was a raw egg, which it isn't, what would the graph do at that point?
Just
stop.
stop.
It would just stay at zero, right?
Yeah.
So the ball is gonna hit, it's gonna slow down, and it's gonna slow down very rapidly, right?
Yeah.
So the next question is, at this point, okay, what's the velocity of the ball? Zero. So this graph can do one of two things. It could slope back down, or it could slope up.
Up,
Gotta
down,
slope up.
down.
Down, why?
Because it goes up and then it goes back.
What?
Because it hits the
Oh,
ground.
Gavin.
Hits the ground.
Oh, Gavin, shut.
Gavin.
Right? Wait.
What is he saying?
It's gonna bounce. The line's gonna
Wait,
go
no,
up,
it's gonna go
and then it's
up.
gonna
I
turn.
lied.
It's gonna.
I forgot we hit the ground. I'm thinking too far ahead. That's all.
okay?
It's gonna go up.
He's thinking of a double bouncer now.
So it's gonna go up like this, right?
Yeah.
So
Yeah, thing go up.
at this point, as it was falling, it was speeding up. True?
Yeah,
Is it supposed to be
It hits
straight
the
or
ground.
angled?
Now what's it gonna do?
start slowing down.
It's gonna slow down very rapidly, right?
Yeah,
The velocity is 0. What's it doing?
changing the direction.
Changing direction. So this is where you have your change in direction. Cool.
It's when it hits the ground.
Now, at this point, what's the ball doing? Speeding up or slowing down when you're in this region up here?
Speeding up.
S-
Speeding
Speeding up. I can't go
Speeding up.
slower than 0,
Yeah.
okay? So it's speeding up. Did the ball change direction at that point?
Yeah.
Yes. How do you know?
Because
So
it's
it's not
not
on
Zero.
Velocity changed the sign and it went through 0. Okay? So I approached 0 very rapidly. I hit 0 and then I sped back up. Okay? So all of this is happening. This is when that ball is in transitioning because it's in contact with the ground. That happens, boom, very quickly. That's that 1.28 times 10 to the minus second. That's that very small amount of time between when it hits, the ball slows down, and the ball speeds back up. Now, at this point up here, the golf ball has left the ground. When the golf ball leaves the ground and it's going up, what's the sign of its velocity? Positive, because we're defining up as being positive, right? So it hits with some negative velocity. You have some positive acceleration, which is going to make it slow down. You have more positive acceleration, which is going to make it speed up.
Where was the acceleration? Sure.
What?
Brother,
It's speeding up.
it's speeding up going upwards.
You're at 0 velocity right here, right? The line, you have to have positive acceleration with positive velocity to make it speed up.
But the only force is gravity.
No, it's hitting the ground.
Is that add force? Oh, it does.
Mm-hmm.
I'm just overthinking it right now. I don't know.
Okay. Now, at this point, it's going to leave the floor. Okay? When it leaves the floor, what's the sign of the velocity? This is important.
Positive.
Positive. So it's going to leave with some positive velocity. It's going to hit with some negative velocity, but it's going to leave with a positive velocity. Okay? Now, is the positive velocity here bigger or smaller than the negative velocity it had?
Smaller.
Small.
Smaller.
How do you know it's smaller?
Because it lost
Because
when it hit.
But how do you know?
Because it's
Because it's
at
not gonna go as
1.85
high.
and
It's
then
not
it
going to go as
bounces.
high. Okay? It's only going to go up to a height of
1 meter.
1 meter. What's the only way it can bounce back up to 1.85 meters?
An
If
additional
you-
force.
If it was-
Put force on.
Like-
Well, no. Just mathematically, it
No
would
If
have.
there was,
Gravity?
if there was, if there was,
No.
No gravity.
If there
No,
was,
no.
no, if
If
there's,
there was no gravity, it would just keep going up.
if
Oh,
there was
energy.
no energy loss.
Yeah, if we didn't lose any energy. If the ball took off with the same velocity that it had when it landed. So if it hits at like -8, it would have to take off at +8 to go back to that same height. Okay? But it doesn't. It only goes up to a height of 1 meter.
So the form.
So here's what I know about this velocity when it leaves. It's a positive velocity, but it's less than the velocity that it had when it hit the ground. So here's what I know. This is why you think through the velocity time graph first. It's going to hit with some negative velocity. It's going to very rapidly slow down. It's going to rapidly speed back up. Then it's going to leave with some positive velocity that's less than the velocity that it had when it hit. So let's say it hits at -8. It might take off at like +6. Okay? And again, All I'm talking about is the value of that velocity. Don't get hung up on the signs and go, oh, -8 is less than +6. Okay, you're not in a math class. All the positive and negative is doing is defining direction. Okay, don't get hung up on like the number line definition of greater than or less than. So at this point, it leaves the floor. What's the graph going to do?
Up.
Wait, when
It's
it
gonna
leaves
start
the floor, right?
This is when it leaves the floor.
It's
And
gonna
it starts
slope down.
sloping
It's either going to slope up or it's going to slope down.
Down,
Starts
slope
sloping
down.
down towards zero.
It's going to slope down?
Yeah.
Why?
Because there's no,
Because there's.
gravity's the only force acting on it.
Gravity's the only force acting on it. So as
Yeah.
soon as it leaves the ground, what does it begin to do?
Slope.
Slow down. So, are these two lines, here and here, parallel to each other?
Yeah.
Yes, why?
Because they have the same acceleration.
Because they have the same acceleration, because the only force acting on it is what Dylan said, which is
Gravity.
gravity.
Yay.
So this slope is also
Negative 9.8.
1.8 meters per second squared. Okay? So if you were to find that area, what would that area equal?
The displacement would.
The displacement,
Yeah.
right?
The 1.5.
This area here would equal the displacement on the way up. Which area is going to be bigger, going down or going up?
Going down.
Because you know that because it falls 1.85, but it only bounces up to a height of
1 meter.
1. Okay? Cool. Now, let's talk about how we're going to find, we need to find that impact velocity right there. So, you got to go old school. Do you know anything about how long the ball is in the air when it falls?
No.
No. But do you know how far it falls?
That
Yeah.
equation.
Yeah.
Yes. Do you know the initial velocity?
Yeah.
You know the acceleration,
Yeah.
but you don't know time. So what are you going to use?
That equation.
Ah, that equation. So I got v squared equals v naught squared plus
2AX.
2ax, right?
Yeah.
Old school. Now, listen to me very, very, very carefully, okay? We're defining the ground as being the reference point. So when that ball hits, right, it's going to hit at 0 meters. What's its initial position?
1.85.
1.85 meters. Now, going back to the lab from yesterday, how do you calculate displacement knowing initial position and final position?
Final minus the final.
Final minus initial. So since my final position is 0, and my initial position is 1.85, my displacement is
Negative 1.85.
-1.85 meters. Now, that's important because that negative displacement matches our velocity time graph. Because we have a negative area, because we have negative velocity multiplied by time. Okay?
Yep.
Got that going for us.
Yep.
So, when it's dropped, okay, so this is going to be my drop calculation. When I drop it, do I know my final velocity or do I know my initial velocity? I know my initial velocity is going to be,
Zero.
so this is just going to be v equals the square root of 2ax. Now, what I'm going to do is wrong. Do not do what I'm about to do. So this is going to be the square root of 2 times negative 9.8 meters per second squared
That's not
times 1.85 meters.
It's negative.
It has to be negative.
Horrible. Why?
It has to be
Because the
negative.
1.85 has to be negative.
Okay, because if you do this,
It's gonna be,
you're going to
It's
have an
gonna have
imaginary
imaginary
velocity.
we don't
Because
want
you're going to
that.
have a negative sign underneath the radical. But this is what I'm going to look for on the test, okay? If you have this, you have to show all these calculations in great detail. If this is what you write down, I'm going to write, imaginary velocity. Cool, okay? No, but if you come in here and you make that negative so that you're consistent, with how the problem is defined,
Cause then they cancel.
then it's all good,
Yay.
because then you get a positive value. Now, so somebody crunch this into your calculator, let me know what you get.
I got 6 meters per second.
No, exactly,
I got
4.2.
I got 6.02 meters per second.
6.02.
That's what I
Dylan, are you plugging it all in at once?
Yeah, I did it wrong,
There's your
actually.
problem.
I forgot to multiply by 2.
It's okay.
Now, is that cool as my velocity?
Sounds about right.
It sounds right, yeah. Well, no,
Bad,
no.
it's bad,
Very bad.
very bad.
What?
Negative,
Why?
because you're dropping it.
Well,
It's
yeah,
going
because
down.
which direction is it going when it hits the ground?
No.
Down. If you leave that as positive 6.02, you're gonna tell me the ball is gonna hit the ground going up. But what's the square root of 4?
2,
Or
negative 2.
negative 2. So
Oh,
you just have to choose the negative root. Okay? We're not making up math. We're not violating any laws of algebra.
Yeah,
We're
I don't
just
think
gonna
there are laws
choose
of algebra.
the negative root.
So
Okay?
I can just throw a negative there and you won't count off?
No, you
Plus or
have
minus,
to.
Gavin.
Oh, okay, okay.
Because if you leave it as positive, you're gonna tell me the ball is going up in the air when it hits the floor.
Anything that comes out of
The
the square root
floor
is
is
plus or
moving to
minus.
No, it's not.
Yeah, it is.
Yes.
I'm kidding.
Okay.
No, you weren't.
Now, so at
I
this
had always
point,
tough one all days.
here's what we know. That point of impact right there is negative 6.02 meters per second. Okay? So when it hits the floor, that's negative 6.02 meters per second.
Indeed.
Now, what we need to figure out next is how fast it's going when it leaves the ground. Now, before you do any math at all, is that positive velocity going up going to be bigger or smaller than 6.02?
Smaller.
Smaller. If I get a number bigger than 6.02, I've done something wrong. Okay? I've done something wrong. Now, on the way up, do you know how far the ball goes?
Yeah,
Yes.
1 meter.
Do you know the acceleration on the way up?
Yeah.
Yep.
Yep.
Yeah.
What's the only thing you don't know?
Time.
Initial velocity or final velocity?
Fine.
Final.
No.
Initial.
You know what the final velocity is. What's the final velocity on the way up?
0.
0. You're trying to figure out how fast it has to go to end up to a height of 1 meters.
Mhm.
So what are you going to use?
That equation
You're
again.
going to use that equation again. Okay? You're going to use that equation again.
It's not the final.
But it's sketchy though. So you have v equals v naught squared plus 2ax. This is on the way down. This is on the way up. On the way up, are you searching for the final velocity or the initial velocity?
Initial.
Initial. So I need to solve this for initial velocity. So what are you going to do?
Square root.
V squared minus,
V.
2ax.
and then the square root of that is going to get me V naught. Okay? I expect to see this written down. Okay? You
Do I
want
have to
full
write down
credit
that
on this
equation?
problem, on this test. I need to see this.
I have a question.
What?
Do I have to write down that equation first and then
No,
write
you,
that down?
you can just solve it if you want.
Okay.
But I want to see this.
Do we have to square velocity or can we just
No, I'm
like
gonna
cancel
do
that?
Way more.
Just
Initial.
hold on.
Way more annoying.
Hold on.
It's
Okay.
subtracted by something.
Now,
No.
on the way up, what's your final velocity?
0.
0. So this is going to be 0 squared. That's important. Because we have 0 squared minus, now is my acceleration still negative 9.8 meters per second squared?
Yeah.
Yeah.
Yes. So that's still negative 9.8 meters per second squared. But the 1 meter,
Leave it positive.
is that positive or negative?
Positive.
Because it's going up, right?
Yeah,
You're
yeah.
going from 0 to 1. Final position 1 minus 0, you get positive 1. So this is why that 0 is important that you leave it in here. Because then I've got 0 minus a negative value. which makes it
Positive.
positive.
Mm.
Okay? So that's why it's so important that you leave that zero underneath that radical. So that way you don't end up with a negative underneath the radical. So, run the numbers, what do you get?
I got 4.43 meters per second.
Sounds
4.43,
Yeah.
okay?
Wait. Yeah, that sounds about right.
Now, does that fit with what we said was gonna happen?
Yeah.
Yes.
Yes, it's a positive value, but it's less than when it hit.
Well, yeah.
So this is gonna be up here.
So does the floor just
4.43.
like take that energy?
Meters per second. Okay? Now, here's the end game. This is what we're after. But this is the trickiest part of this problem. I know that when it hits, it's going in negative 6.02. When it leaves, it's going to take off at 4.43. So I need to find the change in momentum of the ball, listen to me very carefully, when it's in contact with the ground. Not while it's falling, not when it's on the way up. I'm trying to find the change in momentum when it's in contact with the floor, because that's the point of this story, okay? So that's going to be mass times V minus V9, okay? So I've got my mass, 0.254 kilograms. So here's the question. When it's in contact with the ground, is which one, the negative 6.02 or the 4.43, is the initial velocity?
Negative 6.02.
Right, okay? Because it's going to hit at negative 6.02, it's going to take off at 4.43. So this is going to be 4.43 meters per second minus, now,
Minus and negatives.
minus a negative
6.02.
meters per second. Okay? So this is where it gets tricky. When you use that equation and you find the final velocity, which was negative 6.02, the final velocity here becomes the initial velocity when it's in contact with the ground.
Yeah, that makes sense.
And the final velocity the initial velocity that you find on the way up becomes the final velocity in transition with the ground. So V becomes V naught becomes V. That's the trickiest part of this whole thing. So, this is going to be the change in momentum of the ball. 0.254 kilograms. So somebody do the math. Take 0.254 times whatever you get out of that.
I got 2.65.
2.65?
Yeah. Ali, what did you get?
I didn't do it.
Okay? Can I find the force exerted on the ball?
Yep.
How?
Dividing time.
By time.
Which time? The time it's in the air
Change in
Change.
time.
or the time that it's in
The
contact
one
with
with
the
the
ground?
triangle.
Time it hits the
Yeah.
ground.
Contact the ground.
Only the time that it's in contact with the ground, because that's just what I'm focusing. I'm trying to figure out the force exerted on the ball by the ground.
Oh,
Okay? And that time I gave you, so you know force times time equals change in momentum. We have the change in momentum. Now, does it make sense that since time is positive value, does it make sense that the force exerted on the ball is a positive value?
Yes. It's going up.
So it starts to go up after it hits.
Yeah, so when the ball comes in contact with the ground, which direction is the force exerted by the ground?
Upwards.
Upward, okay? I'm not gonna make the ball bounce up by pushing it down, okay?
That'd be
So
pretty cool.
you know the force from the ground has to be a positive value, okay? Because that's the direction that it's acting. So, at this point, we know the change in momentum of the ball, 2.65 Newton seconds. So, and that equals force times time. So I divide that by time, I get my force. So this is just a rate function. When you take change in momentum and dividing it by time, all you're saying is that this is the rate at which the momentum changes. Okay? It's a rate function. So in this case, my change in momentum was 2.65 Newton seconds. And the time was what,
28 times 10 to the negative 2.
times 10 to the minus second seconds. The seconds cancel out. I get force. And I get a positive force. Okay? And I get a positive force. So what do you get when you do this division?
207.4.
So call it 207 newtons. That's the force on the ball. Okay? Now, if momentum has to be conserved, the ball hits the earth. So if the change in momentum of the ball is 2.65 Newton seconds, what's the change in momentum of the earth?
Same amount. Or
Same amount,
but
Opposite.
but a negative value. So the change in momentum of the earth is negative 2.65 Newton seconds. Now, this is one of the questions that I just gave back. And the question was like, if I push on this and I actually slow down, is that a violation of the law of conservation of momentum? Okay? And it's not, because I'm on the earth. So when I do this, okay, I've technically changed the momentum of the earth because the earth has made me slow down. Is it going to make any difference to the momentum of the earth? No. It isn't like, oh man, the earth sped up today. A bunch of people were rolling across the floor in their office chairs. Man, we got to counter that. Tomorrow we're going to make everybody push those chairs in the opposite direction to slow the earth back down. Okay? No. Now, when we have had like massive earthquakes or massive tsunamis, it has changed the rotational speed of the earth. Anything appreciable? No. But it has. And the earth has actually slowed down, which is kind of a cool thing, because they think at one point, like a day, instead of being 24 hours, was actually about 12 hours. So we were spinning like twice as fast, so you'd have like 6 hours of night, 6 hours a day, 6 hours a night, 6 hours a day.
That means
way
we'd be in
less.
school less, right? Oh wait, no, because there's
you
double
just
the
more
day.
days.
It's still just,
Shucks.
we would be the same amount of time.
A week
Dylan.
would be 14 days.
Oh, did you hear about the big earthquake in the Philippines?
No.
Like a while ago? I mean, a couple weeks ago?
I know they just got hit with this.
Yeah, they got hit with a tsunami like yesterday or something.
Well, no, that was actually like a typhoon.
Yeah, well,
What's the difference?
A typhoon is just.
It's a hurricane,
A
but
typhoon is a
backwards.
hurricane in the southern hemisphere.
but
They call
Do
it
they
typhoons.
spin the other way?
yes.
Ooh.
But
So
the
there's-
earthquake that they got hit with, their tremors are like still on a magnitude like 4.2 on average.
Even the aftershocks.
Yeah, like 3 weeks later.
Wow. Some God, I
Like-
know, that's weird.
Those are bigger earthquakes than
Oh,
We
those are
get-
bigger tremors than we get earthquakes here.
Oh, absolutely. Okay, so I know the force on the ball.
Why would you do that, Dylan?
I know the change in momentum of the ball. I know the change in momentum of the earth. Do I know the force exerted on the earth then?
Yes.
Yeah.
What's the force exerted on the earth?
Negative 207.
Negative,
207.
why?
Because it's equal but opposite.
What's Newton's third law?
But opposite.
Yeah, so if the earth exhibits an upward force of 207 newtons, by rationale and Newton's third law, the force exerted in the opposite direction has to be the same value but negative. Can I find the acceleration of the ball?
Yeah.
Do I know the force exerted on the ball?
Yep.
Yeah.
Do I know the mass of the ball?
Yep.
Yeah.
0.254.
Don't we already know the acceleration?
No.
No.
Oh, I thought it
This
was
is when it's in contact with the ground, not
Oh.
when it's in fall. So the acceleration is going to be, so somebody takes 207 newtons and divide that by 0.254 kilograms.
814.9.
815.
So 815 meters per second squared,
What?
right?
Oh.
So,
Now, how does that 815 fit on that velocity time graph?
That's the slope of.
that's the slope of,
Oh, that's that really big sloping line when it's in contact with the ground. Notice that that's a positive value. So that positive 815 made it slow down. Then that same acceleration made it speed up. Okay? So, cool. So the slope of that line is 815 meters per second squared. Nice. Okay, one last thing to do. I've got the acceleration of the ball, 815 meters per second squared. I want to find the acceleration of the Earth.
Just flip the sign.
So here's the question. Is the acceleration of the Earth negative 815 meters per second squared? Hopefully not.
I think we
That'd
got
be
it.
bad.
That would be bad, because if the accelerations are equal and opposite, every time I drop that ball, what would the Earth do?
goes crush.
It would accelerate out from underneath us at 815 meters per
Oh.
second squared. Okay? Basketball season would be horrible, because every time someone would bounce a basketball,
Cheer would be bad too.
You would need a,
yeah, I mean, anything
Anytime
that
you drop a
involves
person on
you would
the
also
floor,
need
it's
like
just.
a lot,
balls in the Earth.
you could also need like a lot of.
Police have their hand clean.
So, could I find the acceleration of the Earth?
You already know it.
No, I don't.
Negative 207 divided by.
Oh, yeah, no.
I'm gonna take negative 207 newtons and divide that by the mass of the Earth, 5.979,
Okay.
times 10 to the 24th kilograms. Hopefully, I get a really small number.
It's a
so
small
the Earth
number?
accelerates it's like,
I just made the Earth accelerate.
keep on doing it, what we move. Like, if you just keep on doing it,
No.
all day long.
Oh, I got a really tiny.
Isn't there like a
What'd
thing
you
where it's
get?
like if you like hit
Negative
Negative
3.4621174.
Just say all the.
Times 10 to the what?
Negative 23rd.
Negative 23rd meters per second squared.
Yeah, what if you just did that like,
That's really, it's really small.
Mr. Bird, isn't it true that there's like a chance like if you like hit your hand on the table, like your hand could like go through it?
Yeah, we talked about.
There's
that
a very, 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 it's calculable, but it's really not ever gonna happen.
3 decibels.
you could also.
So like if I just sit here my whole
It's
life
like-
and
it's
I
never gonna happen.
feel like.
So,
shucks.
here's the story. This is what I want you to get out of this problem. So first and foremost, if there's ever a problem that you go back and rework before the test, work this one.
Should be this one.
What's the only thing that I can change on this problem?
The height you drop it
I
from.
can change the height that I drop it from, I can change the height that it bounces to, I can change the time that it's in contact with the ground, and I can change the mass of the ball. That's it, okay?
What if we did it on the moon?
The only
No
thing
bueno.
changed, the acceleration would be 1.63, but it's still the same idea.
Bro?
So you know this problem is gonna be on the test. You know it is, okay? Don't sit there when you get the test like, man, Burkamp didn't tell us about this. God, he's a jerk, okay? I have it on video, I'm telling you, okay?
Vanessa.
Make sure that you can work this problem, okay? It's already on there, don't touch it.
Take the SD.
Okay, so here's what I want you to get. Anytime you have a collision, the changes in momentum are always equal and opposite. The forces are always equal and opposite. Are the accelerations equal and opposite?
No.
No, okay, because that would be
Shucks.
bad.
That would be horrible.
What's the only way the accelerations could be equal and opposite?
Same mass.
If the masses were the same, okay?
Mm.
That's the only way the accelerations could be the same. Okay, so that's it. For the rest of the time, I've got a video that goes through how crashes play out. So stop that.